All right, then let's kick it off, folks. It's 7:01. I'm late. That's unacceptable. Welcome, everyone, to the July general meeting of the Central Florida Astronomical Society. I am broadcasting from a new location tonight, so what could possibly go wrong? Let's see if I can actually change the slide. Oh my gosh, it worked. If you're watching this and you're not yet a member of the Central Florida Astronomical Society, what are you waiting for? We offer many benefits to our members, including access to private events and dark sky viewing locations of our own when weather permits, of course. We have an awesome loaner telescope program where you can check out a telescope and try before you buy. And also, breaking news, remote observing. So we have a C-Star telescope out at a Texas dark sky site that just got up and running today, which is very exciting. And we can actually, we're working on setting up a system to schedule time on that for our members. So stay tuned for more details on that. But that is actually moving ahead quite nicely. We saw the first images from that today, and it works, which is awesome. We also have a vibrant online community on the Groups.io platform, so members can talk shop with each other. Quarterly meetings at the Seminole State Planetarium. How cool is that? As well as our monthly Zoom meetings, which you're watching right now with our guest speakers. Your membership also includes membership in the Astronomical League for free as part of your benefits. And you also get to feel warm and fuzzy because we're a 501c3 nonprofit organization. Every penny of your dues goes toward our mission and not to anyone's pocket. And you also get discounts on Astronomy and Sky and Telescope magazine for staying up to date on the latest astronomy news. If you're interested in learning more or in joining, head on over to cfas.org to learn more at our awesome award-winning website. Thank you, Rob Fleming. Tonight's agenda, our guest speaker tonight is Professor Robin Metcalf from York University, who will be presenting Astrosleuthing in Aurora, talking about the science of auroras and their role in ancient history, which should be fun. She is currently teaching a class until 7 p.m., so I might segue into club news before we have her on, but that's fine. And after that, we do have our Astrophotography Showcase with a surprisingly high number of contributions, given the weather. I don't know how y'all are doing it, but we've got some awesome images to share with you tonight. And we'll welcome our guest speaker as soon as she pops in. And meantime, I'm going to skip ahead to club news. So we do have our Geneva Dark Sky Nights resuming in September. I'm currently working with the Seminole State staff to renew our agreement for using that site. It's all been drafted and whatnot. We just need to get the final signatures and whatever. They have all the necessary paperwork they need. So that should be happening smoothly. Why September, you may say? Well, during the summertime, it's just not a good time to observe, quite frankly. There's a lot of clouds, a lot of storms. There's not a whole lot of daylight. So we kind of throw in the towel for a couple of months there. But those will be back in September. And of course, members are always welcome to gather on their own and communicate on Groups.io. And if you just want to get together at a dark sky site of your own, like Chiefland or whatever happens to be nearby, Bull Creek, whatever you want, just throw out a note there and see if anyone wants to join you. There's nothing wrong with that. Also, I want to thank Emily Chung for stepping up as our new social media chair. And if you've noticed a few more posts on our Instagram page, that's why. So thank you, Emily, for volunteering for that. And if you have any social media ideas you want to forward along, you could contact her at social@cfas.org. Thank you so much, Emily. And like I mentioned, our remote C-Star access in the Texas Dark Sky Observatory site is going to be available to you real soon now. It is actually up and running. We just have a few final kinks to work out, and we have to work out the mechanics for scheduling time on it and education. So stay tuned. That is going well. Also, John Frank's still working on a member survey for 2025, so keep an eye out for that. We want to hear from you about what you want to get from the organization and what we can do better. And we do listen. You know, we actually did change our direction quite a bit last year in response to the survey we got last year. For those who volunteered at the Final Frontier concert on June 6th, thank you so much. That was a smashing success from what I hear and fun for all. Summertime, again, is kind of a slow time for outreach, but we do have a few things lined up, mostly at the Orlando Science Center. So if you do want to get out there and be a little bit of a advocate for space, there's an opportunity to do so at OSC's Astrofest on July 19th and 20th, also August 16th to 17th at the OSC Engineering Weekend, and August 23rd for the Orlando Science Center Science Night Live. And if you want to get involved with that, join the outreach subgroup on Groups.io for more information at that link there, or just email our outreach chair, Doug, at outreach@cfas.org. Also, we're starting to think about the holiday party. Believe it or not, I know it's only July, but a lot of work goes into that event. So when we have our next board meeting, we're going to start talking about the logistics of that. Speaking of the member survey, something we heard a lot of feedback from last year is that people were frustrated that they couldn't get in, that we had limited attendance. We only had so much space. We only had so much budget. So this year, I think we're going to be charging a nominal fee for that event, so we can actually expand access to that and afford a larger venue and more space for everybody. We're working out the details, so stay tuned on that. And also, didn't quite make the slide, but the Orlando Museum of Art has reached out to us for another collaboration, by the way. So more details on that soon. They're doing another little space exhibit there, and they want our support in providing some props and materials for that. So breaking news there for you. Also, welcome to our new members. Saw a lot of you at our last in-person meeting, so thank you for joining. If you are new, make sure you read that Welcome to the Central Florida Astronomical Society letter you got along with your new membership. There's a lot of important information in there. It explains how to access our community platform on Groups.io and explains all of your member benefits that you want to take advantage of. If you have any questions as a new member or an old member, whatever, you can contact me at president@cfas.org or our board members at large. Their function is to be the liaison between the membership and the board of directors. That's Wes Clem at bmal1@cfas.org or John Pinto at bmal2@cfas.org. And if you're interested in serving on said board, we are always looking for new help. We do need a new loaner program chair to step up for Chris. And I think we have a few candidates out there right now. So I think I'm cautiously optimistic about that one. We also have openings currently for publicity and education if you're interested, or whatever you want to do. You can serve on a committee and do whatever you feel like doing. The existing committees can always use an extra hand and extra people to kind of learn the ropes for future roles. So if you want to get involved in events, programs, outreach, treasurer, science website, membership, observing, whatever you want, make up your own position. I don't care. Let's hear from you. Let me know at president@cfas.org. Also, remember, we are a 501c3 charitable organization. So if you or your employer is looking to make some charity happen, head on over to cfas.org/donate, where we will gladly take your sponsorships and corporate donations. Also, if you work for the Mouse, Disney has this in their Cyber Grants platform, where you can actually do matching donations through Disney and any other one who's on the Cyber Grants platform. Upcoming astronomical events. So we are in the summer Milky Way season, which means some really cool nebula are in the sky tonight if the clouds happen to clear for you. For example, the Lagoon Nebula, seen here on the right, one of my favorites. Of course, the summer clouds are here as well, so you have to get lucky. But fear not, we have our darker, more cloud-free remote site in Texas for that very reason. Again, stay tuned for more on that. Also, the mornings tend to be a little bit more clear here in Central Florida, so if you're an early riser, you might be able to catch a glimpse of something cool. A few interesting astronomical events coming up in July. So on July 12th, Venus will be rising along with the red star Aldebaran in the morning. And then we have a series of conjunctions with the moon. So July 15th, the moon and Saturn will be close to each other. And then on the July 20th, the moon will pass by Pleiades. On the 23rd, it will pass by Jupiter in the morning. And on the 28th, the moon will be near Mars. Always a fun thing to watch or maybe even photograph if that's your thing. And I'm going to get back to the Astrophotography Showcase after I check if our guest is here.
I am here.
Sending a private
message.
Are.
Great, thank you. I'm just trying to find you in the list. Go ahead and unmute yourself and turn on your video. I think you should have
My
access
video is
to
on.
screen share.
You
Great.
should see a background of Tatooine.
There you are. Hello, welcome.
Thank you.
All right. All right. Hope that class went well. Let me give you a brief introduction here, and then I'll hand it over to you if you want to share your screen and
Sure.
do your presentation. So joining us tonight is Professor Robin Metcalf of York University, presenting Astrosleuthing and Aurora. Robin Metcalf is a professor at the Division of Natural Science at York University, where she's been teaching physics and astronomy courses for over 20 years. Robin's PhD research pertained to extragalactic astronomy, but her current interests are in the search for life beyond Earth and the implications of such a discovery on humanity. Through her teaching, Robin shares her passion for the night sky and the outdoors. She teaches students to appreciate what the night sky has to teach us, to gain perspective from our place in the universe, and to value our precious planet Earth. Well, I think we're all on the same page there. So quick housekeeping before we get started. If you have any Q&A questions for Professor Metcalf, please drop that in the chat box here for the organization, or use the raise hand icon if you want to ask your questions live. And do please stay on mute during the presentation if you would. With that, I will hand it over to Robin Metcalf.
Thank you. Okay, so let's share. Awesome. You can see the presenter view?
Yes, there we go.
Okay.
Just popped in. We're good.
Okay, thank you so much for the introduction and thanks for the opportunity to meet your group. Before I get into the topic for this talk, I'll just tell you a bit about what I do. So I'm an astronomy prof at York University in Toronto, which is in Canada. I've been here for over 25 years, and I'm also currently the director of York's Division of Natural Science. And this is the department that is responsible for offering science courses specifically designed for non-science majors. So it's purely for engagement in science. We offer about 50 of these courses, pretty much every branch of science you can think of. And those of us that get to teach those courses in our respective disciplines, we absolutely love it. I find it to be the most meaningful and rewarding teaching that I can do because it gives me the chance to ignite an appreciation for not just the night sky, but also the outdoors and how important it is for us to preserve this awesome and precious planet that we all share. So all of my time these days is taken up with teaching, departmental admin, and public outreach whenever I can squeeze it in, volunteering at star parties and giving talks to various astronomy clubs such as yours, which is something I love doing, but much more so in person when I have the opportunity. Still, I'm glad we're able to do this virtually. Prior to all of that stuff, though, I conducted research for about 10 years in extragalactic astronomy and large-scale structure, meaning the study of other galaxies beyond our own galaxy, beyond the Milky Way, and how that extragalactic matter is distributed throughout the universe. So, more specifically, I was part of a near-infrared imaging survey of about 100 of the nearest dwarf irregular galaxies for the purpose of mapping out their distribution in 3 dimensions and investigating different cosmological models of how that distribution of galaxies came to be. So on the slide is one of the papers that came out of that research published under my maiden name. And you just see some examples of our galaxy images and brightness profiles. Okay, so that is enough about me. Let's move on to the topic of this talk, which is the awesome phenomenon known as the aurora, what we call the northern lights here in the northern hemisphere. And over the past year, I've given a few talks on this topic, owing to the fact that we are currently experiencing a period of time in which aurora are seen far more commonly than usual, and not just at high latitudes, which is where we are far more used to seeing them, but also at mid latitudes, such as where I live in southern Ontario. And so over the past year, we've seen aurora in my part of the world on several occasions. Many of us have seen them for the first time. And on the side, you see a photograph taken by one of my fellow night sky enthusiasts from Wellesley, Ontario. Wellesley is a suburban area. It's only about 1.5 hours northwest of the city of Toronto. And yet, despite its proximity to a whole lot of light pollution, the aurora could still be seen with the naked eye. When I was in Florida in May, I actually learned from another astronomy club that aurora have recently been seen in your part of the world as well. But of course, more typically, if you've seen an aurora, you were very likely at a higher latitude than where we all are right now, either high up in the northern hemisphere or low down in the southern hemisphere. We're going to talk about why that is as we go through the story of how we came to understand the cause of an aurora. And a lot of that stuff you might already know, but after that, we're going to get into some of the really cool ways that scientists can trace aurora back by thousands of years, even before recorded history. And hopefully in that portion, there'll be something new for you to learn. Before we get into that, though, we're first going to look at just a few of the ways that aurora have been interpreted by different cultures and how that has led to the diversity of names that aurora go by. So the widely adopted scientific term for the northern lights is the aurora borealis. That term came from the Italian astronomer and physicist Galileo. Galileo would have been able to see them once in a while from his mid-latitude hometown in northern Italy. And Galileo described the northern lights by following the tradition of naming celestial phenomena after gods and goddesses in Greek and Roman mythology. And so he chose the name Aurora Borealis, Aurora because that is the Roman goddess of the dawn, the bringer of light. and borealis after Boreas, the Roman god of the northern wind, to reflect the movement of the lights, as though the glow is sort of being blown by the wind. You can get a sense of that in this real-time video. This is a photograph of an aurora seen from Churchill, Manitoba. Churchill is at a latitude of 58 degrees north of the equator, and at those higher latitudes, aurora are seen more frequently and they tend to have a more vibrant appearance. So in this photograph, in addition to the green glow, we can see some purples and some faint pinks. To the OG Cree, who are one of the First Nations in this part of northern Canada, the aurora are called Wawate, and they were believed to represent the spirits of the ancestors. Sometimes the lights were seen as the spirits issuing a warning or an omen of some kind, or sometimes the lights meant that the spirits are dancing with happiness or laughter. It just depends on the context of the observer at the time. This photograph was taken from Stewart Island, which is the southernmost region of New Zealand at a latitude of 47 degrees south. We can also see there, unfortunately, I don't have a pointing device, but we can see our two nearest galaxies, those smudges, known as the Large and Small Magellanic Clouds. And in this southern part of the world, the aurora are known as the aurora australis, which comes from the Latin for southern dawn. But to the indigenous people of New Zealand, the Maori, the aurora were given a name which translates to burn in the sky and refers to the reflections of the campfires built by the ancestors. So again, we see this connection drawn with the spiritual realm, and that theme is found in the names given by many other cultures as well, all reflecting the sort of ghostly appearance of this phenomenon. Now, of course, aurora have been lighting up the skies for far longer than humans have been around to witness them and to describe what they saw. But the first suspected written account of an aurora goes quite far back to nearly 3,000 years ago in ancient China. And this discovery was made from a translation of an ancient Chinese text. So you see the text on the right. The text was found on bamboo slabs known as the Bamboo Annals, which is on the left. And what the translation says is, in the last year of King Zhao, during the night, a 5-colored light penetrated Ziwei, which refers to the northern side of the sky. In this year, the king inspected the southern regions and did not return. Okay, so it's kind of ambiguous, right? Like, you might think a 5-colored light, that could mean all sorts of things. So why is that suspected to be an aurora? You know, the description doesn't even give us a sense of how defined this light was in the sky. Maybe it was a comet. Maybe it was a really bright supernova. Any of those events would be consistent with what historians have learned about the ancient Chinese astronomers. We know that they were tasked by the various ruling dynasties with recording anomalous events in the sky. So, for example, things like comets and eclipses, because in the 10th century BC, in this part of the world, it wasn't yet understood that those events actually follow a regular predictable cycle. And so instead, those sightings were believed to be unpredictable events that reflected chaos on Earth, something as chaotic as, say, the king disappearing. So we can at least conclude that this text is referring to something seen as highly unusual in the sky, which is reasonably consistent with the appearance of a comet in these times, but also with an aurora from the latitude of this sighting. Because the latitude of this sighting is only around 34 degrees north, and aurora are hardly ever seen at latitudes so close to the equator. The aurora that you see in this photograph on the slide, it was actually taken from the northernmost region of China at a latitude of 52 degrees north of the equator. But the rare aurora at lower latitudes does occasionally occur. And when they occur, they actually leave behind these little clues for us to find in some really interesting places. And later on, I'm going to show you the evidence to support that claim. For now, I'm going to leave this mystery hanging for just a bit and take you instead to the story of how humans discovered the cause of aurora. And it's a neat story because it involves some serendipitous discoveries as well as some interesting problem solving. Okay, so I'm going to start close to the beginning of the story, but not at the actual beginning. And we're going to first look at a little piece of the puzzle that came from radio astronomy, just because it's a neat little warm-up story. Okay, radio astronomy, of course, just refers to observing the sky by looking at the really long wavelengths of light that celestial bodies produce, as opposed to the relatively short wavelength light that the human eye can actually see. So radio waves, we know they're typically like billions of times longer in wavelength than visible light waves. In fact, radio waves are so long in wavelength that they can pass through our atmosphere virtually unimpeded. They are so much larger than the particles that make up our atmosphere that they just pass right over those particles like they're not even there. And so those radio waves that make it all the way to our radio detectors, our dishes that are on the ground. So owing to the ability of radio waves to easily pass through the atmosphere, they have a long history of use in the military dating back to World War II, when radio waves were used to detect incoming enemy ships and aircraft using the technique known as radar. But radar had one unfortunate weakness, which is that it's possible for the enemy to scramble or jam the incoming radio waves that are searching for them. And you can see that in this wartime illustration. So if warplanes are transmitting radio waves in a certain pattern, then those radio waves will interfere with the waves that are coming from radar transmitters on the ground, and that will prevent anti-aircraft guns from being able to accurately pinpoint where the warplanes are coming from. So in 1942, after a series of incidents in which German warships were using radar jamming to make it through the English Channel undetected, a British radar operator named Stanley Hay was tasked with developing anti-jamming methods. And so Hay studied these jamming patterns carefully. And on 2 days in February of 1942, he received reports of a particularly severe jamming signal. And the signal had the curious behavior of seeming to follow the motion of the sun, as the sun was moving westward across the sky throughout the day. Now, that could have just been a coincidence, but Hay decided to investigate whether anything interesting was going on with the sun on those days. And so Hay contacted the Royal Observatory in Greenwich, England, where astronomers observed the surface of the sun on a regular basis. And here is what Stanley Hay learned. The Royal Observatory reported that on those days in question, an unusually large dark spot was seen on the surface of the sun. And this is something we call a sunspot. And in this slide, you see a recent photograph of sunspots taken from a beautiful provincial park a few hours north of Toronto. It's called Killarney Provincial Park. And the park has its own observatory, owing to the fact that it's located in a designated dark sky reserve. So Stanley Hay had made the connection that sunspots emit radio waves, which we receive here on Earth. 3 years after Hay's discovery, so we're now in 1946, a group of Australian radar operators reinforced Hay's findings using a new technique known as radio interferometry, and that enabled them to produce an actual image of the sun in radio light. And they were able to show that wherever we see sunspots in visible light, we see intense radio emission at the same locations as the sunspots. So on the slide, these are recent photographs of the sun taken at the same time, in visible light on the left, radio on the right, and you can see the clear connection between sunspots and radio emission. So Hay's discovery was essentially the beginnings of radio astronomy, because it was the first time that radio waves had been connected with an object beyond Earth. But the discovery is also important in the context of understanding the aurora, because as you're going to see, by studying all the types of light from these eruptions on the sun, both the visible and the invisible light, we've obtained a better understanding of the cause of these eruptions and also how they affect us here on Earth, which is how the aurora story comes in. Okay, so let's move on to an earlier and much larger piece of the aurora puzzle, to a discovery that was made in 1908 by an American astronomer named George Ellery Hale. So Hale, was able to show by looking at the light around the sunspots that they are magnetic. meaning that if we had an enormous horseshoe magnet and we brought it close to a pair of sunspots with opposite poles facing each other, that our magnet would be pulled toward the sunspots. So here, can you, sorry, I'm limited to a small screen, but I think somewhere I have the planet Earth. Is the Earth up at the top?
Yes.
Okay, good. So you can see the planet Earth, it's added to the image for comparison and drawn to its actual size relative to these spots. And that just gives you a sense of how monstrously large these sunspots can be. They're like the sizes of worlds. So in any case, Hale's discovery showed us that the sun has a magnetic field. It is in itself a giant magnet. And what we've learned about the sun over the years is that its magnetic field has a cycle to it. And that cycle is what led to our understanding of the aurora. So let's talk a bit about magnets for a moment. At some point in your lives, you likely saw this kind of experiment where you've got tiny bits of iron ore poured over a bar magnet, and instantly the iron bits redistribute themselves into a pattern that reveals the magnet's magnetic field. So we see curved lines that begin and end at each pole. And at the poles, the iron bits are most concentrated because that's where the magnetic field is strongest. Now, if we were to go out into space and dump an enormous pile of iron filings all over our planet, the same thing would happen. The iron filings would trace out the magnetic fields very similar to the field of a bar magnet, with magnetic field lines going in and out of the Earth's north and south pole, because that's where our magnetic field is the strongest. And why is that? Where does Earth's magnetic field come from? It's generated by the churning motion of Earth's liquid iron core. So that core is essentially a giant bar magnet. It's a natural geodynamo, and the field around that magnet extends well beyond our atmosphere. Okay, so that's the Earth. What about the sun's magnetic field? What does its magnetic field lines look like? Well, given that the Earth's magnetic field is generated by the churning motion of its fluid core, and given that the sun itself is a giant churning fluid, then one clue as to the sun's magnetic field must come from its spinning motion. And in fact, when we measure the rate at which the sun rotates around its own axis, we find a big clue to its magnetic field, which is this. If we monitor the sun from hour to hour, we're going to see that its sunspots move, as you see on the slide, simply because they're moving with the sun's rotation. So by tracking the sunspots and measuring how long they each take to traverse the sun's surface, we can get at the sun's rotation speed. When we make that measurement, we find something really interesting, which is that depending on the latitude of the sunspot, so how far they are from the sun's equator, the rotation period changes. The closer the sunspots are to the equator, the faster the sun's rotation period. So you can see that on the slide. It takes far fewer days for sunspots to get around to the equator than it does up at the poles. So what this is telling us is that the sun is composed of gaseous or fluid layers that spin at different speeds. And this is known as differential rotation. And that is unlike our planet Earth, which is mostly solid, and that gives the Earth a much simpler rotation. Earth spins at the same speed, roughly the same speed everywhere. So you can imagine if you start with a spinning bar magnet, and then you slice it into horizontal layers, and each of those layers are spinning at a different speed, then the magnetic field lines are going to get messy. The magnetic field at the equator is going to move faster than the field at higher latitudes, and that's going to cause the field lines to skew. And eventually, the field lines at the equator are going to outlap the lines at higher latitudes. And over time, that's going to cause the lines to get all twisted up. They're going to push and pull on each other with such ferocity that some of those magnetic field lines are going to get pushed right out of the sun's surface, making loops that go in and out of the sun. You can see that in this computer-generated illustration. And when that happens, energy gets released from the regions around the holes in the form of radio waves, as well as higher energy light, like X-rays and ultraviolet light. And these days, we can actually see that happening using space telescopes that can see in the X-ray and the UV. So here's an example. This is an ultraviolet photo of the sun taken from space by NASA's Solar Dynamics Observatory. You can actually see how the ultraviolet light traces out those magnetic loops poking in and out of the sun, owing to charged particles from the sun's surface being dragged through those loops, and that causes them to radiate. So it was that behavior of light in and around the sunspots that Hale had detected, invisible light, leading him to make the connection between sunspots and magnetism. So at these high energy wavelengths, at the entry and exit points of the loops, we see bursts of intense light, what we call solar flares. Whereas when we look at the sun close up in visible light, as you see on the right, we see that those high energy bursts of light coincide with the dark sunspots. And as for why the sunspots appear dark, that occurs because the strong magnetic fields in those regions, they're disrupting the flow of heat. And so you can see that in this diagram. The green circles are convection directions, and then the black dashed lines are magnetic field lines. And so you can see how the convection of heat below the sunspots is disrupted by the field lines, and that causes these regions to cool down and not glow as brightly as the rest of the sun. It's just like when a stove element cools down, it loses its orange glow and it turns black. But when we say cool down, that's just in a relative sense. These regions around sunspots, we're still talking about temperatures of like 4,000 degrees Celsius, which of course is not cool at all, but only in comparison to the rest of the sun surface, which is like 6,000 degrees Celsius. Okay, so these days, solar physicists can produce computer simulations of the sun's magnetic field. You can see one on the slide. And what we see from these simulations is that the sun's differential rotation creates a crazy, distorted mess of magnetic chaos. But underlying that chaos, the cause of it, is an orderly process in the sense that the rotation speeds of each of the sun's layers, they might vary with latitude, but they don't change with time. Each layer rotates at essentially a constant speed. And that means that there must be a pattern to the chaos. There has to be a cycle in which, after a certain number of years, the magnetic field lines get all wound up and then they unwind before getting all twisted up again. A simple way to decipher that cycle is to track the sunspots. Because if sunspots are caused by the sun's magnetic field getting all wound up, then if the winding follows a cycle, we could expect the number of sunspots to follow a cycle as well. When the sun is most wound up, we're going to see a lot of sunspots and vice versa. So that is exactly what was found by a German amateur astronomer named Heinrich Schwab. Schwab counted the number of sunspots seen over a period of around 2 decades, from the 1820s to the 1840s, and he found that the frequency of sunspots follows an 11-year cycle. You can see that this in the slide, this is a more recent graph of sunspot numbers, so that's SSN, seen over a 250-year period. And you can see every 11 years or so, we experience these peaks. We experience a 1 to 2 year period in which, at any given time, we see significantly more sunspots than normal. And so when we look at visible light photographs of the sun during one of its 11-year peaks, what we call that a solar maximum. So you see that on the right, we see an active sun, lots of sunspots, whereas during an 11-year minimum on the left, we see a quiet sun, typically some sunspots, but not nearly as many and usually not as large. And of course, since the sunspots coincide with solar flares, when we compare UV images of the sun at solar maximum to solar minimum, as you see on this slide, we see numerous intense flares during a maximum on the right and only a few little sparks here and there during a minimum on the left. So the sun can get quite stormy with its sunspots and flares, and we now know that that activity affects us here on Earth. Scientists on Earth who continually monitor Earth's magnetic field have observed that every once in a while, the Earth's magnetic field seems to get scrambled. And on the slide, you can see a graph of this. So Normally, the strength of the Earth's magnetic field tends to remain pretty steady, but once in a while it can go all over the place for a time. So that's that messy bit that's going on in the middle. And if we happen to be looking at a magnetic compass at that same time, you would see that the compass needle would just suddenly go crazy. It wouldn't be able to find the Earth's North Pole or the Earth's, the North Geographic Pole until the Earth's magnetic field goes back to normal. So how do we know that these geomagnetic storms are somehow connected to solar storms? The proof of that came in the 1850s when it was found in the records of geomagnetic storms over the decades that there's a cycle to their behavior, and not just any cycle, but a roughly 11-year cycle, and an 11-year cycle that pretty closely coincides with the 11-year sunspot cycle. So the blue bars here show the number of geomagnetic storms over a 150-year period, while the red lines show the number of sunspots over that same period. And you can see there's a reasonably strong correlation between the frequency of the peaks in both graphs. So that connection between the Earth's magnetic storms and sunspots made it clear that the sun's stormy periods are affecting us here on Earth 150 million kilometers away. So something is coming out of those solar flares besides light to be able to distort the Earth's magnetic field. And so by combining what was learned about the sun's magnetic field and the emissions from sunspots, the underlying physical process emerged, which goes like this. When the sun's magnetic field lines poke out of the sun releases solar flares in addition to charged particles, electrons and protons. And in fact, the sun is always ejecting charged particles. We know this because they were actually detected from space by a spacecraft in 1959. We call that the solar wind. But when they come from sunspots, they're ejected in particularly intense and localized bursts. And so those are known as coronal mass ejections, or CMEs. So these bursts of charged particles, or plasmas, they shoot off in all directions, but some of those bursts head toward Earth. And what we know about charged particles is that they are essentially tiny bar magnets, simply because they're spinning particles with electric fields. And when electric fields spin, they generate magnetic fields. So when a plasma hits the Earth, it's like dumping a bunch of iron bits on our planet. The charged particles get caught in the Earth's magnetic field lines and they get pulled down toward the Earth's poles, because that's where Earth's magnetic field is strongest. While at the same time, the magnetic fields of those charged particles, they cause the Earth's magnetic field to distort. And that creates those geomagnetic fluctuations that we measure here on Earth. So finally, then we can put all the pieces together and see what this has to do with aurora. As the charged particles from the sun are pulled into our atmosphere, particularly at the poles, they collide with atoms in our atmosphere, atoms like oxygen and nitrogen. And as a result of those collisions, the atoms, so those are the purple symbols there, the atoms get excited. They gain energy from the charged particles, but then over time, the atoms run out of steam and they relax back to their normal state by giving up the energy that they gained. And that energy is emitted in the form of light waves. So that's the light that produces an aurora. Now, why the different colors of an aurora? The different colors occur because different atoms emit light at different wavelengths when those atoms de-excite. You might have seen this done, or maybe you did it yourself once in a science lab, where you're given a sample of sodium or calcium powder and you put it in the flame of a Bunsen burner to heat it up. That excites the atoms. And then you observe that as the atoms de-excite, the different substances turn the flame different colors. So similarly, when charged particles from the sun excite the different types of atoms in our atmosphere, those atoms will also emit different colors when they de-excite, depending on the strength of the ejection from the sun. So, for example, since the oxygen atom only needs a bit of energy to produce a green glow, green is the most likely color that you're going to see in a typical aurora. However, if the ejection from the sun has some strength to it, it will also excite the nitrogen molecules in our upper atmosphere, which will produce a red glow. Same thing for hydrogen and helium atoms, which only exist in small amounts in our atmosphere. So again, we need a really strong solar ejection to bring out their bluey purplish glow. And then by that point, you've got all these light waves getting mixed together in our atmosphere, producing all sorts of cool hybrid colors like pinks and orange and yellow. So this is why when you're at high latitudes on Earth, aurora tend to be more colorful. So the image on the top that was taken from Iceland, because at high latitudes, Earth's magnetic field is strongest. So that's where the bulk of the solar particles get pulled toward. But if a solar eruption happens to be really strong, you can get colorful aurora at lower latitudes as well. One important thing to note, though, is that people who have seen aurora with the naked eye will most commonly report that they appear whitish. And this is just because our night vision isn't as good at discerning individual colors as the detector in a camera. If you think about what we see at night, everything kind of looks gray, right? We can usually tell the difference between the grass and the road, but not because the grass actually appears green at night. It's more likely that we can just make out that grass has a different texture than the road does. So all those really colorful photographs of aurora, they do in fact match the colors that are being produced by our atmosphere. It's not our camera playing tricks on us, but it's just that at night the human eye doesn't work as well. It tends to perceive those colors less vibrantly. So since aurora are caused by solar activity, they have the same 11-year cycle as the sunspots and the geomagnetic storms. Every 11 years during a solar maximum, when the Earth is bombarded by solar storms, we see lots of aurora, and they appear more intense and colorful, as well as at latitudes further from the poles, closer to the equator. Whereas during a solar minimum, aurora are less frequent, less intense, and pretty much confined to the Earth's poles. Now, sometimes eruptions from the sun can be particularly intense, and when they reach the Earth, our atmosphere can become so charged up that it can affect our ability to communicate. During really intense solar storms, we can and have experienced disruptions of power grids and satellite communications, including GPS systems, which so much of our infrastructure now depends on. So there's a lot of interest in learning as much as we can about these extreme solar storms. Maybe we can discover a pattern or some sort of early warning sign. And since they don't seem to happen very often, we need to look for them in the past, as far back as we can. And that's why it becomes important to determine whether these 3,000-year-old ancient records do in fact refer to an aurora, especially records like this one of glowing lights in unexpected places, because those are most likely, if this is an aurora, then it is most likely to be caused by the extreme geomagnetic storms. So to see how we can sleuth out whether an ancient record refers to an aurora or not, we're going to go even further back in time than recorded human history to possibly the strongest known solar eruption to date, which occurred over 14,000 years ago. Now, how on earth could we possibly know that? Here's the evidence on the slide. This is an article that was published in the Journal of the Royal Society in 2023 by a group of French researchers. And in the abstract, we find this statement that the resulting carbon-14 record exhibits an abrupt spike occurring in a single year at 14,300 calendar year BP. BP just means before present. The correspondence with beryllium-10 anomalies allows us to propose the event as a solar energetic particle, or SEP, event. So translation, solar eruptions leave behind little coded messages on Earth in some very interesting places. Okay, so here's where we get into the really good stuff, and this would be a good time to drink some coffee or Coke or wine, but whatever it is that you have. While we sit here in this quiet, seemingly peaceful virtual space, our planet is being bombarded by high energy particles from outer space. We call these cosmic rays, and they come from all sorts of high energy things happening in the universe, like supernovae, galaxy collisions, black hole mergers, or they can come from solar eruptions. In high enough amounts, cosmic rays are dangerous for humans. They're high energy radiation capable of damaging human cells, but the Earth's awesome magnetic field deflects most cosmic rays. And those that make it through will interact with particles in our atmosphere, causing the rays to weaken in intensity and kind of fizzle out as they get lower in our atmosphere. Now, when cosmic rays interact with the molecules in our atmosphere, chemical reactions take place in which the products can be radioactive. So you see an example on the slide. This is showing you the production of the cosmogenic radioactive isotope carbon-14. Cosmogenic simply means produced from cosmic rays. And radioactive atoms, they can come in very handy because they enable us to do something called radiometric dating, or in the case of carbon-14, it's more commonly known as carbon dating. To see how that works, let's first quickly address what radioactive actually means. So a radioactive atom is simply an atom with an unstable core. The core of an atom, its nucleus, that's where most of its matter resides in the form of protons and neutrons. And between those particles are all sorts of little forces that cause the particles to push and pull on each other. As long as the protons and the neutrons are arranged in a nice uniform way, those forces will all balance out and the nucleus will stay stuck together forever. But there are some forms of atoms where the distribution of protons and neutrons is not nice and uniform. And a particularly important example is a form of carbon called carbon-14. Carbon-14 is an unstable form of carbon because it's got two more neutrons than it should. And those two little neutrons create a very slight instability, such that owing to the dark magic that is nuclear physics, one of the neutrons somehow converts itself into a proton and then shoots out an electron in the process. And that causes the carbon nucleus to actually morph into a different atom. It becomes nitrogen. So because carbon-14 has this behavior of decaying, shooting out particles, we say that it is radioactive. Okay, now why is that useful? It's because every radioactive atom has an exponential rate at which it decays, and those rates can be measured. In the case of carbon-14, its decay rate is such that whenever carbon-14 is created in the atmosphere by cosmic rays, it begins to decay. And 5,700 years later, the number of carbon-14 atoms will have been reduced by 50%. So we call 5,700 years, that's the half-life of the carbon-14 atom. So if we find a sample of carbon-14 in some substance on Earth, and we measure that its population has been reduced by 50%, we've just learned that the substance it formed in is 5,700 years old. And no matter what population drop we measure, we can plug it into this known decay rate for carbon-14, and we can determine the number of years that have elapsed since the substance formed. So in other words, radioactive elements like carbon-14, they provide us with this very important gauge of measuring the age of substances over time spans longer than human history. Okay, so back to the cosmic rays. When cosmic rays interact with our atmosphere, they produce two types of useful radioactive atoms. They produce carbon-14 and beryllium-10. Like carbon-14, beryllium-10 has two extra neutrons, causing similar instabilities in its nucleus, but it has a half-life of nearly 1.5 million years. So it's still unstable, but far less so than carbon-14. So what happens to these cosmogenic radioactive atoms? The carbon-14 atoms, they eventually attach themselves to oxygen and they form carbon dioxide. Carbon dioxide gets absorbed by living things on Earth, trees, animals, humans, and that makes all living things on Earth slightly radioactive, though it's It's really not anything we need to worry about, the fact that we're radioactive. It is what it is. But meanwhile, the beryllium-10, it has a very different fate. It quickly gets swept up into precipitation, and it's delivered to Earth inside either raindrops or snowflakes. So that's how evidence of solar activity can get transported to Earth and stored in places like trees and ice. But in order to actually learn anything from those atoms, there's still some decoding that we have to do. So let's first see how this is done with trees. You've very likely seen samples of tree trunks in which there are visible rings, and you are likely aware that the rings can be used to deduce the tree's age, simply because each year a tree grows a bit thicker, and because that growth varies in appearance depending on the season, each annual layer is clearly delineated. And that enables a dendrochronologist to measure the tree's lifespan just by counting its rings. Now, we just saw that cosmogenic carbon-14 is absorbed by trees as they grow. And we saw that carbon-14, that we can use carbon-14 as a gauge of age. A dendrochronologist can therefore measure the carbon-14 abundance in each ring and use that to anchor each ring to a specific calendar year. And so you see that done in this sample on the slide. So in 2022, a group of researchers did that analysis on a very special group of trees. And these are trees near a riverbank in the southern French Alps. They had been buried by sediment at the end of the last ice age, about 10,000 years ago. So they were deprived of oxygen and therefore preserved in time, even though their carbon-14 kept ticking away, keeping track of the years. The trees were eventually discovered after years of erosion, and the carbon-14 analysis revealed that they're over 14,000 years old. So what that analysis also revealed is a sharp spike of carbon-14 in the year 14,300 plus or minus 1 BP. So again, BP means before present, where present is standardized as the year 1950. The magnitude of the spike corresponds to a 30% increase in carbon-14. And if that is coming from a solar eruption, that spike would make this the strongest known solar eruption to reach the Earth. So how definitive is this? Does this spike really represent a surge of cosmic rays from the sun, or was it caused by some other source of carbon-14 that has nothing to do with solar activity? How can we corroborate this with entirely independent evidence? What we can do is we can look at another cosmogenic probe of cosmic rays, which is beryllium-10. As we saw, beryllium-10 is brought to Earth in precipitation, and in the really cold places on Earth where precipitation freezes and it collects from year to year, we can get our hands on ancient ice. And if we can somehow connect the ice to specific calendar years, then we should find that in roughly the same years that we see spikes in carbon-14, we should also see spikes in beryllium-10 if the carbon-14 spikes do indeed correspond to cosmic rays. So let's see what the ice tells us. Every winter in the really cold places on our planet, so places like Antarctica and Greenland, it snows. Most of that snow melts away in the summer, but in those really cold places, the summer season is typically so mild and short that not all of the snow melts. And so you get layers of leftover ice that pile up on top of each other. And each of those annual layers contains information about the state of our atmosphere at the time that the snow melted. So scientists have drilled deep into those ice deposits, and they've pulled out cores of ice that are like 3 kilometers in length, from which they can reproduce the atmospheric conditions of our planet out to nearly 1 million years ago. And the study of those ice cores is known as paleoclimatology. Now, the way that data is extracted and decoded from ice cores is extremely cool. Just like with tree rings, The number of layers can tell us roughly the time span of a particular ice layer. But if we want to connect a layer to a specific calendar year, then we need, like the tree rings, we need some way to anchor the layers to real time. And amazingly, the cores themselves contain that information. You may have seen this for yourself if you've ever hiked inside of an ice cave. So see those black layers, those are ice layers that formed during a year when a volcanic eruption occurred. A volcanic eruption that spewed ash clouds into the atmosphere, which fell back to Earth in precipitation. And since we know the specific years of the Earth's major volcanic eruptions by dating volcanic rock, those black lines are like a chronological ruler that are embedded inside the ice core, like a clock inside of an ice core. And here's a photograph of a segment of one of these cores showing a particularly strong ash layer on the right there, from which a calendar year can be deduced following the sequence of ash layers along the full length of the core that this was cut from. And then each volcanic layer is assigned a calendar year, and that enables us to assign specific years to the other layers in between the volcanic layers, typically within a precision of plus or minus 10 years. But it gets worse as you go further and further back in time. So the resolution of this method, it's not as high as you can get from the tree rings, which are like within plus or minus a year, but it's still high enough to capture any really dramatic events in the atmosphere that may have occurred in a particular decade. So what do the beryllium-10 levels tell us? Using an ice core that was drilled out of Greenland in 2005, paleoclimatologists have constructed the history of beryllium-10 levels out to 60,000 years in the past. And just like with carbon-14, we see a spike in beryllium-10 at roughly the same time and roughly the same relative magnitude as the carbon-14 spike. But in this case, we're seeing the spike in a region on Earth nearly 4,000 kilometers away from the trees in France, as you would expect for a global cosmogenic surge from the sun. So using these kinds of tools and strategies, whenever we find human records of unusual glowing lights in the sky, we can look for evidence of intense solar activity in places like ice cores and tree rings to establish whether or not the written records were indeed describing an aurora. Now, back to why studying these ancient aurora records continues to be important. The historical records show us that powerful solar storms have occurred during solar minima. It turns out that a quiet sun doesn't mean it's entirely inactive. It still can stir or snore once in a while. And for example, in May 1921, a strong geomagnetic storm was reported to have caused all sorts of electrical problems on Earth. And as you can see in this graph at the bottom, it's showing sunspot numbers over the 20-year period before and after this event. The peak of that storm occurred near a solar minimum when the sun had no business waking us all up like that. So the more data we can get on these really strong ancient flare-ups, perhaps we can discern a cause or even a cycle to the really strong surges and get a better idea if this is something that we really need to worry about. And if so, what should we do to protect ourselves from what the media has referred to as a potential internet apocalypse? But maybe that wouldn't be such a bad thing. It would force us to look up more and enjoy the night sky and get off our screens. Anyway, so where are we currently in the 11-year solar cycle? As I'm sure many of you already know, we are somewhere within a solar peak. You can see that on this graph. The curved red and gray lines are showing us that the next predicted peak is occurring right now in 2025. And those curves just come from computer modeling of the solar cycle. But those black lines come from actual sunspot counts. And what's interesting is that the current sunspot counts are significantly higher than predicted by the model, by nearly double the predicted amount. And that's showing us that our understanding of what's going on inside the sun, it's not as comprehensive as we thought that it was. There's obviously more factors at play which impact the number and intensity of solar storms. So we still have quite a bit to learn about this awesome star, which we depend on for the survival of all life on Earth. Now, having said that, we do have some ability to make predictions about how the sun's behavior affects us on Earth, because when a solar storm occurs, we can use the Earth's magnetic field as an aurora alert system. By constantly monitoring fluctuations in Earth's magnetic field, which is done by organizations like the NOAA, the National Oceanic and Atmospheric Administration in the US, we can identify periods of particularly intense geomagnetic activity because those periods can last several hours. And we can use that as a forecast of a particularly good night for aurora watching. And just like meteorologists will use the UV index as a measurement of the ultraviolet light that the Earth receives on a particular day, scientists who track Earth's geomagnetic activity, they use what's called the KP index. The P stands for planetary, and the K comes from a German word that essentially means numeric index or digit. So the KP index is a number from 0 to 9, where high numbers mean intense geomagnetic activity and therefore high likelihood of intense and low latitude aurora, whereas a low KP index means aurora are less intense and more likely confined to high latitudes. On any date and time, you can go to a site like the NOAA Space Weather Prediction Center and see a visual map of the KP index showing you where on Earth aurora are most likely on that particular date. And so on the left, you see the aurora forecast during a solar minimum. Green means a relatively low probability of aurora. On the right, you see the forecast during a solar maximum. Red means high likelihood of aurora. And you can also see how the auroral region, it covers a greater area going down to lower latitudes. So this is an exciting time for those of us who love the beauty of the night sky. As I mentioned at the start of the talk, there have been an increasing number of aurora sightings in southern Ontario over the last year. And as a result, many Ontarians, including myself, have now seen an aurora for the first time. And that has led to some interesting adventures for those of us who chase these kinds of things. So, for example, on May 10th of last year, the sun was sporting a particularly large and active sunspot group, which you can see on the slide. These are actual photographs from May 10 from last year with a zoomed in view of this monster storm on the left. And not surprisingly, the measured activity from this storm led to a spike in the KP index starting at around 6 p.m. Now, as it happened, that evening I was at a monthly meeting of the local astronomy club that I belong to. And so a bunch of us hopped in our cars and we headed northish, about a 45-minute drive from Toronto, to an area we knew of that was reasonably free of street lighting. Now, it's important to note that no one in this group had ever seen an aurora before, so we were quite excited and maybe a little overeager about it. Shortly after we got to the spot, one of us pointed out a noticeable bright patch in the western sky. We all aimed our cameras and phones at it, and we had a massive group freak out when the exposures revealed that bright pinkish blob, which we interpreted as an aurora breaking through the clouds. However, as we clicked away at that blob and we waited for it to dance the way that, aurora are supposed to, what happened a few minutes later was this. There was no change to the shape of the blob. It just turned this very suspiciously artificial looking blue. Now, at this point, one of us looked more closely at our location and found that in the precise direction of that auroral blob was a casino, very likely shining a colorful spotlight into the sky. So in our collaborative embarrassment, we all promised each other that we would never tell anyone about that mistake. You can see, how well I've kept that promise. But more importantly, that night was not a complete failure. We hopped back in our cars, we drove a little bit further north, and as the roads got darker, we came upon a bunch of cars that were all pulled over by the side of the road. And we got out and we saw, unmistakably this time, huge gray vertical streaks all around the north side of the sky. Unfortunately, I only had my old cell phone on me at the time, but a 1 second exposure revealed that. This absolutely blew my mind. And one of us in the group did have a DSLR with them and was able to get a bunch of stunning photos, including this one. What I love about this photograph is that it really gives you a sense of how intense the storm was, that we were able to detect it with the naked eye in a suburban area with was not entirely dark. There were streetlights where we were. I'll leave you with one more very special photograph that was taken during that same solar storm by another member of our astronomy club who's a little bit further north from our location. And what's so special about this photograph is that it caught a rare type of aurora that none of us even knew existed. According to the photographer, he saw what looked like vertical oscillating beams all around the sky in greens and purples that were visible to the naked eye, but of course not as vibrant as in the photo. And when he followed the lines upward, they converged at a point directly overhead. And we later learned that that is a rare phenomenon called an aurora corona, or an aurora crown, which occurs when the auroral activity is peaking directly over the observer. And the event was bright enough that the photographer was able to capture it with just a 1/2 second exposure on his cell phone. So just when we think we've seen everything that the sky has to offer, it can still have these amazing surprises for us. And that is it. I hope you enjoyed the talk. I hope you all at least learned at least one new thing and that it got you excited about what the night sky has in store for us over the rest of this year as we ride out this solar maximum together. Thank you so much.
Thank you, Robin Metcalf. That was great. And I think we all have Aurora envy at this point. We technically had some Aurora down here in Florida last year, but it was just like a faint red glow if you
That's
took
what
a
I
long
heard.
exposure. Yeah. Couldn't see it
Yeah.
with the eye. That's actually a question that I have. Like, why was it red and not green down here?
Okay, so that's a really good question. The red colors are produced primarily by the nitrogen in our atmosphere. And there's a lot more nitrogen in our atmosphere than there is oxygen, like 75%. And so if the aurora burst or if the solar burst is strong enough, then it does have enough energy to excite more red than green. So that is why you were able to see more of the red. It's just, I don't know that that's the entire answer to the question because where I'm at, I have not been able to see the red. I've only seen the green. So there's something else going on. Um, yeah, but that is as much as I can answer at this time.
Cool.
But the
Thank you.
red comes from the really, really strong bursts.
Hmm. Guess that's the ones that reach this far down, maybe. I don't know. Yeah. Do you have time for a few questions?
Yeah, I do. And now that I think of it, it might also have to do with altitude because the higher you go, like if you go up a mountain or whatever, the higher your altitude, the stronger the bursts are. So if you're high up on a mountain, you're far more likely to see red. And I wonder if the altitude where you saw the red is higher than where I'm at. I don't know what the altitude above sea level is for
Oh,
Florida, but maybe that has
0.
something to do with it. Oh, yeah,
Yeah.
yeah, that would make sense. We were pretty close to the ocean.
Yeah.
Yeah. Oh,
Yeah.
well, so much for that explanation.
The only mountain we have is Space Mountain at Disney World. So,
Right.
yeah.
That's true.
Yeah. Cool. All right, we got some great questions here. So let's
Sure.
start with Jeffrey Martin here, who asks, "What will be the consequences to our communication networks if the Earth's magnetic fields flip in the near future?"
Sorry, if the Earth's magnetic fields split, or is that
Flip.
the question? Or if we just have like a really, really strong burst? Or are we talking about a different phenomenon with the Earth's
Well,
magnetic field?
Yeah, go ahead, Jeffrey.
yeah, I've read like every 500,000 years the magnetic field flips. The
Right.
south
Oh,
goes to
oh,
north,
flips.
north goes to south. How is that
Yeah.
going to, will that have any consequences with our technology, communications, or?
Yeah, you would think so because GPS systems is all based on compass directions and being able to find us. It's very gradual. And in the time of human civilization, we have not had a no really measurable change in that movement of our magnetic poles. So I don't know that we've ever really thought about having to compensate for it. But I mean, humans are pretty smart, so I'm sure that we could figure out a way to do that calculation
Okay.
once the shift actually becomes noticeable. But as far as the flipping, it wouldn't make a difference. It's just this gradual effect of the motion of the shifting of Earth's magnetic poles. The fact that it flips is like it doesn't just instantly flip, right?
Oh, okay.
Yeah, yeah, yeah.
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 I've watched too many movies. Hollywood.
Sure, you could do some really fascinating science fiction if there was a sudden flip. That would be pretty freaky. But that cycle that you mentioned, hundreds of thousands of years, is so long term that it's just a gradual shifting of our magnetic poles from one side of the Earth to the other.
All right. We've
Yeah.
averted one less catastrophe.
One less thing to
Mhm.
worry about.
Thank
Yes.
you.
I'm actually curious what that would do to auroras too. Does that mean that auroras would shift their position around the Earth as it flipped?
Exactly. Yeah. So as our poles move, our magnetic poles move, then the likelihood of aurora is going to change to different latitudes. And in fact, that the Chinese sighting, that's what that whole article is about, is that they worked out where the North Magnetic Pole was at the time of the sighting, and they found that it was 5 degrees closer to the latitude of the sighting. And so it wasn't such an anomaly
Hmm.
because by moving further north, it made that latitude a little bit more likely to get aurora.
Interesting. Cool.
Yeah.
Yeah.
All right, we have another question here. Did Galileo witness the phenomena prior to providing a name, or did he only hear of it? Yeah, did Galileo actually see an aurora?
He actually saw it.
Hmm.
Yeah, that's a good question. I had to do a lot of digging to find that information because I knew he named it. And I was like, well, how did he know that? Was it just based on travelers telling him? But I did come across a story that said that he was able to see it on occasion. And it does make sense from the latitude where he resided.
Okay,
And he
cool.
would have been able to see strong winds during solar maximum.
All right. Got a good one here from Alexander Happel. If Earth orbited a habitable zone of a red dwarf with its intense flares and UV X-ray output, how might auroras appear? Would they be constant or
Oh.
global, and would their color or behavior be different from what we see on Earth?
Wow, that is such a great question. Okay, so if we were in a habitable zone around a red dwarf,
Hmm. That's right.
um, okay, wow, that is such a fun thing to think about. I don't know how quickly I can do it on the fly. So if anyone else wants to jump in, but it really just comes down to what is the cycle of the magnetic field, and that has to do with the spin. So, I'm realizing that these stars produce different emissions, but I don't know that the spin is a constant thing for that type of star. Like, sorry, you said a red dwarf star? Is that
Yeah,
right?
yeah. We get a lot of news about discovering potentially habitable planets around red dwarfs, but then they also come with the
Yeah.
caveat that, well, there's a lot of flares from the star, so maybe it's not so habitable after all, right?
Yeah. Yeah, that's so interesting to think about. I was thinking more about the cycle. But yeah, so the flares and yeah, yeah. I'm just thinking my head's going all sorts of different directions. Are the flares, so the flares are light. That's not what's causing aurora. It's the plasma, it's the coronal mass
Hmm.
ejections.
Okay.
For us, the two go hand in hand because the flares are caused by, the loop splitting, and that's why it's tied to the magnetic field cycle, which is tied to the spin. But do flares on red dwarf stars coincide with plasma ejections as well? That's not something that I know. But if it does if they are, and therefore it is due to the magnetic cycle, then it really just comes down to the spin of those stars. And then the other thing that I don't know is, are the spin of those stars the same for all red dwarf stars because that's what would set the cycle. Among main sequence stars, like our sun, the spins can be all over the place. So, yeah, I can't answer that because there's those two bits about red dwarf stars that I don't know, but it's such a fun thing to think about.
Yeah. It
Yeah,
kind of makes you wonder if auroras are kind of a biomarker of sorts. Can you have life without auroras? Because that magnetic field is kind of necessary to protect the atmosphere, right?
definitely.
Yeah,
Yes.
cool. Awesome. We've got a question from William Castro on kind of a similar vein. Have you done any work with Aurora on other planets? And yeah.
Cool. So you can definitely see some very cool images of Aurora on other planets because all you need is an atmosphere and a magnetic field. And Jupiter has that many, many times stronger than Earth does. So does Saturn. And if you just ask the internet, they will show you some space-based images where you can see it looks like Jupiter has a sort of purple hairdo at its
Hmm.
poles. And same thing with Saturn, but the color glow is different because their chemical composition of their atmospheres are different.
Yep, yep.
Yeah,
Are
but it
there
looks
any
super
examples
cool.
of rocky planets that have auroras other than Earth, or are we it?
Mars has localized auroras. I was reading today. It's
Really?
not a global magnetic field. It's local magnetic fields, and it's diffused across the surface of Mars.
Very cool. And did you is has anyone ever produced an image of that?
Yeah, Perseverance actually took a picture of it.
Hmm.
Really?
Yeah.
Oh, that's very cool. I have to
Yeah,
check
that's
that out
awesome.
and add that to these slides.
Yeah, definitely.
Amazing what those rovers are able to show us.
All right, cool question from Luke Corwin. When did scientists actually realize that aurora were caused by the activity from the sun that you described?
Well, okay, so I'm terrible at remembering years that I've just stated.
18.
Um, but it first began with that connection between so not with the radio wave story, that was later. That was when, solar activity was connected to radio waves. But it was the first, I think it was hail. So it's sorry, I'm zipping past the flash to try to remember the year, and probably I'm going to crash if I do this too fast.
Mhm.
But right, so it
What
was before the 1940s,
was it?
and
1908? I think I saw that zip by.
yeah, that sounds familiar. Yeah, sorry, I don't because I can't see my whole screen. So,
Oh, okay. I'm pretty sure it
but
was 1908 if I saw that slide correctly. So,
and there and I went so fast that now it's not moving, but that sounds right. That was with the Hale discovery, right? When he
right.
saw the connection between the cycles
Hmm. Yep.
of sunspots. Yeah.
Right. All right. Wesley Clem asks 14,300 for the largest SEP is pretty recent. How far back can that testing method look?
Can we go further back than 14,300 BP?
Right.
We could if we had trees that if we discovered trees that old, and then again they would have to be preserved. Um, in the ice cores, you can go back even further. Like ice cores can show you the our atmospheric history down to like a million years in the past. But you lose that resolution, and if the resolution is goes beyond an 11-year cycle, right? If it's plus or minus 50, then you're going to lose the surges. So we're probably at about the limit. Unless you can find the older trees, we're probably at the limit
Hmm.
with going back any further than the ice cores, because already that's a resolution of plus or minus 10 years.
Yeah. Yeah, that brings up a question that I had too. Like, how does that event from 14,300 compare to the Carrington event? Because that's usually what's held up as the example of what would the internet apocalypse be today, right?
Yes, so similar.
Yeah.
That's what the article goes on to say that if you measured it, the strength of it would be about the same strength.
Okay, interesting.
Hmm.
Um, the redwoods go back, petrified redwoods at Florissant in Colorado go back 32 million years.
Ah, okay,
I
there you
wonder if
go.
beryllium in those petrified rings of the redwoods would be something they could assay and extrapolate back.
Maybe that would be that. Let's see if someone has now done this. So this article that I showed you is quite recent. It's only 2023, and perhaps that has triggered some activity in trying to find older trees and doing
Yeah,
the
I don't know if
analysis
it.
further back. So that would be pretty cool.
Yeah, I don't know if that would work on a petrified tree though, because that would be measuring like a
Oh,
mineral
sorry.
set.
Did you say they were petrified?
Yeah, petrified redwoods, 32 million years old in Florissant in Colorado.
Yeah. So I don't think you can do it with petrified trees because then you can't age them. Well,
With
wait a
carbon,
second.
but you could like you couldn't use the beryllium deposition in the fossilized
Oh, I
material.
see what you're saying.
Yeah.
Um, yeah. I don't know. That is really cool to think about, and you would get that precision because because of rings. Yeah, I'm not sure.
Hmm. I think Jeffrey has a patent in his works there.
Okay. We've got
Very
a
cool.
Yeah, go get it. Go ahead. That would be very cool. Get on it.
that's a PhD thesis for you. Another
Yes,
There you
one.
let us
go.
know what you find.
Seriously. Alexi mentions that maybe that reddish glow that we see down here is just due to the higher water content that we have down here because of our extreme humidity. That's a decent
It could,
explanation.
yeah, it could be. It could be. Yeah, that's right. So oxygen does produce a red. Uh, yeah, it produces green and red depending on whether it's like, diatomic or whatever.
Mhm.
So yeah, that could be the case.
All right.
And would definitely explain why you saw it and I didn't, because
Yep.
we're not nearly as humid up here.
Must be nice. All right, a couple more. Is there a relationship between auroral color, red for oxygen, for example, and the intensity of the solar activity in addition to elevation and altitude? That question's from Ray Gregory.
Um, yes, in the more intense the surge, the more red you're going to get, and it's because um, uh, I think I was saying this before. So nitrogen is what is the most common molecule in our atmosphere. It's like 75%. That's what produces the red, but nitrogen takes more energy to get that transition to produce the red light waves. And so if the surge is very powerful, you're going to get more red than you would otherwise.
Cool.
Does that answer the question?
Yes, I think so.
Okay.
And Alexander has a question kind of building on that. Has there ever been a solar event strong enough to cause biological harm on Earth? Hmm.
Interesting. Not that I know of. So basically, the only reason why that would happen is, well, let's see, why would that happen? Biological? Yeah, like
Yeah, the
so what's happening? We're ionizing the atmosphere, which has electrical effects on things, but not on people. Um, we're heating up our atmosphere, which is causing it to expand, but not, that's mostly happening at high altitudes, so not anything
yeah.
that bothers us where we are. Yeah,
Well,
nothing that I can think of.
I suppose if the atmosphere expanded and caused a Starlink satellite to fall on your head as a result, that
There
would be
you go.
biological
That would be a biological
harm.
harm.
Yes, that's my answer. All right. And we'll wrap up with William Castro's observation that this is a good time to remember that the Astronomical League, which you are all a member of, has observing programs for hydrogen alpha and the Sunspotter observing program. So if you have your hands on a solar capable scope, go sign up and join the challenge. And with that, thank you so much, Robin Metcalf. That was a great talk and a great Q&A session. Can't thank you enough for your time tonight. Really appreciate
Oh,
it.
my pleasure. Thank you. That was fun.
Yeah, thanks for letting us have you. All right, yeah, you're welcome to hang out if you want for the Astrophotography Showcase or get back to your evening. But again, thanks for being here tonight. We really appreciate it.
Thank you. I
Take care.
normally I would stay, but I am going to sign out because I've had a very, very long day.
I understand.
But
I can
great
relate.
to see you all. Thanks so much.
Thanks so much. All right. And with that, we're going to switch gears to the Astrophotography Showcase. If I can figure out how to share my screen again, I think I just did it. Yay. All right. And I think most of you are here. Let me pull up the participant list. And again, if you are present, you are more than welcome to unmute yourself and talk about your image here. So let's kick it off with John Starr, who's been taking advantage of that same dark skies site in Texas where we just planted a sea star for the club. John, are you here?
Yes, yes. Good evening. So yeah, so this I have really been enjoying Starfront observatories and once you guys get the Sea Star sorted out for everybody to participate, I highly recommend folks sign up to do it. It's really exciting because it feels like cheating. The photos take very little time to collect to collect data, and so this is the Blue Horsehead Nebula. I only have 6 hours of RGB data on this. Now I do have 5 hours of luminance, so it is 11 hours total. But it's impossible to take this shot from Winter Park. This is reflection nebula in general, like this one, are pretty much impossible, or take just an extraordinary amount of time of integration time. And so this was taken with my ASCAR FRA 500 at f3.9 with LRGB Antlia filters on a ZW AM5 mount. And so we've had a few clear nights. I'll tell you, even though it's pretty overcast here, it's crystal clear in Texas right now. Of course, it's almost a full moon, but that's okay with narrowband filters. So.
Yep. Gorgeous. Amazing resolution too. What's your sub exposure time on that?
So one thing, that's a great question. So one thing that I really had to adjust when I started shooting out there was my exposure time. So here, when I shoot in my backyard, I only shoot 2-minute subs when I'm shooting broadband. And here I'm shooting 5-minute RGB and I'm shooting 3-minute luminance. I can shoot way longer for both of those, and the reason I don't though is because I will way oversaturate the stars. The stars will just blow out, especially in luminance. And so sometimes if I'm shooting near a bright star, what I'll do is I'll also shoot 30-second subs of RGB and then just swap out the stars. So I will have to do that. But yeah, you can shoot. I'm shooting 5 minutes RGB and 3 minutes luminance.
Wow. Yeah, those stars are really tight for 5 minutes. So you must have some pretty awesome guiding going on there too.
Yeah, and when I shoot narrowband, I'm shooting 10-minute subs
Mhm.
narrowband.
Yeah, very impressive. And speaking of impressive, you got another one. Oh my.
Yeah, so this is Rho Fuki Cloud Complex. I didn't shoot any luminance. This is 6 hours total, 2 hours in each of RGB. Um, and so I barely did any processing at all, which is shocking to me. When the data is so good, it's so much easier to process. You spend so much time here in light polluted skies figuring out how to hide stuff and fix stuff and all that kind of stuff. But here the data is just so great that it really did not take a whole lot of effort. I did a little bit of saturation, a little bit of contrast, and of course I separated out the stars and processed those separately. But I've never really been able to shoot this quite like this before. Nico Carver, I don't know if anybody follows him on YouTube, but I saw him take a version of this, and I really loved his composition, and so I did. This is close to his, but yeah. But again, this is only 6 hours, so I am shooting other things that are 30 or 40 hours, mostly dark nebula and stuff like that. That's absolutely impossible. But
Mhm.
this is a couple examples of relatively short stuff that you can do.
That's awesome. Yeah, I was kind of debating whether to throw a telescope on the southern hemisphere or Texas, but there's a whole part, there's a whole world of the night sky that is unveiled to you just by being in a dark site. So yeah, you're really taking advantage of that. That's cool. Yeah, that's great. What's the field of view on this, by the way?
So this is the focal length is 350. So I stopped it down. So essentially at 3.9 to collect as much light, mostly because I'm really trying to shoot some very, faint stuff that I could never ever shoot before. It's opened up a whole variety of new targets. And so
Yeah.
I went kind of wide here. I'll tell you though, once you get a scope down there and it's so easy because you just log in and it's clear all the time and stuff, I'm now thinking, do I want to send something down there with a bit more focal length? But this is 350.
Hmm. Awesome. Beautiful, beautiful stuff. Yep, I think you have me sold. Well, you have the club sold because we do have a C star down there right now. So, hey, members, you too can take advantage of these guys soon. Thanks so much, Sean. That's awesome.
Thanks.
Richard Wright, speaking of awesome, you just came back from the Grand Canyon.
Yeah, I sent in two pictures kind of celebrating the Grand Canyon. This is the desert view. My daughter and I went out one night and did star trails. Pretty simple technique. I just took 240 30-second exposures and
Hmm.
stacked them all in Photoshop as different layers, and you set the layer style to lighten, and each image lightens up the one before it, and you get star trails. So then afterwards, I did a little, finagling with Photoshop to tweak it a little bit. But as you can see, we had a lot of people come by, walking
Yeah.
up and down the path well after dark. I made a version without them. Like I just went in and painted out all the lights and the individuals. But I kind of liked it better with the lights, just to show the human activity. So um, yep, there it is.
Cool.
So
Interesting is what you don't see in this image, right? No planes, no satellites, just a few.
there, okay. You're gonna make me confess.
Uh-oh.
I did paint out a Starling train, and I painted out a couple of plane trails. The
Okay.
There's a couple of meteors. The Bootes meteor shower was going on.
Yep.
The two meteors you see most prominently aren't coming from the same radiant, so
Yep.
they're probably just sporadic. But yeah, there were planes, and there was a really brilliant Starling trail went right over the tower, um, in a couple of the images.
Hmm. Cool. And your star colors there are pretty amazing too. Like John Starr just commented on that as well. How do you pull that out?
Yeah, yeah. I didn't have to pull it out too much.
Hmm.
There were 30-second exposures. I think it was ISO 800, and it was like f4 on a 2470 zoom lens. I had it backed out all the way at 24. But I probably bumped the saturation a little bit, but the colors were already there and were already showing up pretty well.
Yeah, that's amazing.
So yeah,
Yeah, stars are not all white people. So there's your evidence.
yeah, yeah.
Cool. And we got this one too. Your very own Milky Way.
Yes, yeah. Mine, all mine is what I called it. So I was with about 100 other astronomers. We were volunteer rangers, and at the end of the star party, when the public starts coming about 11 o'clock, we just have the run of the park and we run amok everywhere. And this is at Mather Point. A bunch of us went out there. There were some couples taking selfies of the couples, snuggling on this rock, and then they were exposed twice. And I thought, well, I'm by myself here, and I'm just going to go up there and stick my arms out and like, it's mine, mine. The whole sky is mine. And yeah, it really was. This is 10 seconds at f1.4, a Tamron 35 millimeter f1.4 lens, and it's a Canon EOS RA, which is
Mhm.
a little bit more sensitive to the hydrogen alpha. So the little pink nebula that are popping out. Um, I did only global adjustments to this, so I didn't do anything to fudge those little nebula. They popped out quite readily with the modified camera. But yeah,
Real cool.
so that's another, nice Grand Canyon. Both of these just tripod shots with a mirrorless camera
Yep. Doesn't have to be
and a
fancy.
shutter release. Yep.
Awesome. Thank you so much, Richard. Sounds like a great chip too.
Oh, it was.
I'm sure. John Sasson, a fellow member from the Space Coast. Check it out. John, are you here?
Yeah, I'm here.
Cool. What are we looking at?
So I took this picture from my backyard here in Melbourne. I tried to get the Crescent Nebula and Tulip here. This is with a Red Cat 51 and a Player One Poseidon OSC. I did use a narrowband filter and I was using Serial and playing around with the pixel math to try to split the hydrogen and oxygen signals from my one color. So it
Yeah,
was fun playing
gorgeous.
around with it. I kind of like the composition of getting both of the kind of famous nebulas in one shot here.
Yeah, those are two of my favorites, the crescent and the tulip. Also, you can see a little faint bow shock of Cygnus X1, I think it is. So that's actually caused by a black hole, which is kind of cool. And I'm going to look up what that blue nebula there is. Do you know what that one is? Down at
No,
the bottom?
I don't. And so this is about like 19 hours of integration. And part of
Yeah.
why I did it for so long is I had another picture where it was just a tulip. And I was noticing that the little blue thing that you pointed out, and I kind of wanted to get more details on it as well.
Mhm.
But no,
Yeah.
I still don't know what it is.
Maybe you discovered something. You got to look that up. That's cool. Awesome work. Thank you so much. And Jeffrey Merrick, what do we got?
Here I am. Can you hear me?
Yes.
Okay. Yeah, that first, I was in Bryce Canyon 2 weeks ago, attending an AstroCon 2025 conference.
Yeah,
So it's like at Rainbow Point. 10 seconds, no drive. Compared to those other Milky Way photos, though, I mean, this isn't good. I mean, even the ones on the presentation look pretty good if you saw that. But anyway, that's my attempt at the Milky Way. Crystal clear skies, something I don't get here in Florida. So
Yeah, that's what's important, the discovery and the sense of awe. But
yeah, this was taken with just a 24 millimeter lens at f2.8.
awesome. Very cool. Yeah, just seeing the Milky Way at all, I think, is always worthwhile because
Yeah.
it's so rare around here. Cool.
Mhm.
Got another one here too.
This is nothing compared to the photo a couple of photos ago. And that's my goal is to try to capture a picture like that, that other one. But this is the road complex.
Yep.
And this was taken, taken with 200 millimeter lens. And I was tracking, and I think I had about, I don't know, 70 subs
Mhm.
at I think it was about 50 seconds or so exposure on the subs.
Yeah.
So I'm trying to get more color. I think the only way to get more colors is to take that IR window out of my camera and put something that is capable of looking at the H alpha lines in that nebula and bring in more.
Yeah, definitely. Yeah,
Yeah,
that would definitely help you have a more specialized camera with the proper filters. But it's also just
yeah,
a matter of exposure time too, So
yeah.
70, an hour sounds like a long time, but that other picture you're talking about was many hours. So
Many
yeah.
hours. Maybe I should
Oh
go
yeah.
with many hours. I don't know.
Yeah, the more the
But
better.
I didn't have much time during the night, so.
Yeah. Ray Gregory's asking about the ISO on that. Do you know?
Oh, yeah, I had the ISO at 5,000.
Cool.
Yeah, because I was trying to capture more of the color.
All right. Thank you.
So
Cool. All right. Wes has a couple of, oh my gosh, that must be the Flame Nebula.
Yep. Flaming Star Nebula.
Yep.
This is probably it ranks up there anyway as one of my favorite objects in the sky. Just like the dynamic movement, the waviness of it. I just always have loved this object. Imaged it for the first time, what, like 3 years ago or so, and I always wanted to come back and revisit it with more focal length, and here we are. This one's with my SCT at about 1400
Wow.
in HSO. And this is about, I think it's about 30 and a half hours, a little over 30
Oh,
hours of HSO. Yeah.
wow. That's amazing. Yeah, it's one of those nebulas that really lives up to its name. It's absolutely a flaming star. My gosh. Beautiful, beautiful stuff.
Thank you.
Thank you. John Pinto's got some sea star goodies for us.
Yeah, so I can't wait to actually try some of these at our storefront. In fact, I'm not sure, Frank, are we going to see any of Chris's test images?
I did not get them into this presentation, I'm afraid.
That's okay. So if you go on Groups.io, he posted the same version of this, but from Starfront, and it's dramatically different. I don't even think he did 10 minutes, and it's better than this. This is just 33 minutes from my backyard. Well, I should say my driveway with streetlights everywhere. So I was really impressed that the Sea Star could pull that off.
Yeah, for sure. Galaxies are very sensitive to light pollution, so we'll have a great advantage in Texas. And here's some cool stuff.
Yeah, so I picked this one, M106, mainly because of all of the little galaxies that are around it.
Yep.
I looked up some of these, and a couple of them are like, I don't know, 300 million light years away. So like those tiny little ones that say NGC 4231, NG 4232, those are 340 million light years away. That's like, that's crazy from my driveway. So
Yes.
really impressed.
It's a time machine back to the age of dinosaurs.
Yes.
And then some. A glob.
Of course, the wild duck. It's just a pretty. I love seeing these open clusters right in the middle of the Milky Way. It just always fascinated by it.
Okay,
That's
cool. Yeah.
if anybody wants to know. Yeah.
M11 and the sun.
Of course, got to do the sun. So this was when we were out at Geneva at the end of May. What I guess one of our last real clear nights in Geneva, and I was just basically just setting up. Right, the sun was still up, and I said, "Well, let me just see what's going on." And sure enough, we had a beautiful sunspot right in the center. So I just love what the Sea Star can do. Just that's like a single shot. That's not even like taking a video and processing it. It was like, oh my goodness.
Yep. And during the solar maximum, no less.
Yes.
And what's this one?
That's your Omega Centauri. Whenever I'm in Geneva in May, I always try to do Omega Centauri. It's just unbelievable.
Absolutely.
I just love that cluster. Now, the only reason I should mention, the only reason why the stars look kind of orangey is only because it's so low in the sky. So you're looking through, heck of a lot of atmosphere. So they aren't really that orange.
The fact we can see it at all is amazing.
Yeah.
Lagoon.
And this was just as I was packing up, and I looked up and I said, "Oh my goodness, the lagoon is up." Like I said, we were packing up, so I only had a few minutes, and I said, "I'll just try it." And 12 minutes got me that, and I was like, "Oh my goodness!" And again, it's because the sky's dark, right? You don't need a lot of time when you have. And again, I can't wait to try this from Texas. This is going to be amazing.
Very soon.
Okay, and then everybody's been talking about this T Corona Borealis that's supposed to go nova. So I figured, well, let me take a shot of it. So where it is, IC 4587 is just a marker that everybody uses to find it. T Corona Borealis is that orange star just to the top right of it, like around 1 o'clock. That orangey star. I don't know, Frank, if you. Yep,
that one.
Yep, that's him. And so he's about 10 magnitude 10 right now. So when he blows his top, hopefully within the next year, that will go to magnitude 2, which will be way brighter than anything in this picture. And it'll be about as bright as Alphecca, which is the second magnitude star within Corona Borealis. So I look at it every morning when I can, just to make sure.
All right, keep an eye on it. Make sure it's behaving.
Yeah.
And the moon.
Yeah, and then of course we have to do the moon. So this was 2 days after full last month. And this one I did do a video and then processed it and sharpened it up a little bit. And I was just amazed how clear a Sea Star, 50 millimeter lens can really bring out a gorgeous image like this. It's just, I'm always impressed.
Yeah, it's an amazing little device for sure. All right, and that's all we got tonight. So thank you, John, and thank you everyone who contributed to tonight's presentation. And thanks for being here tonight. I'll have the recording for this up sometime tomorrow on YouTube, and I'll see you again on Zoom next month with our next speaker. So thanks, everyone. Good night. Keep looking up.